Hello and welcome to helpyourmath.com. In this video, we are going to look at functions and the operations. We're going to talk about sums, differences, products, and quotients. We can combine functions using the four traditional operations by setting up the given operation and simplifying. This will create a new function. The following are equivalent expressions, and let's remember that mathematicians are very lazy. The least amount of writing, the better. The sum function, so we're taking this function f of x, we're adding it to g of x. We can just write it as just this one expression, f plus g of x. So this is the sum function at that point x. The difference function is when we're taking one function and subtracting it by another. And again, we can just look at the functions themselves at that point x. We have the product function, which when we write it as just like that double set of parentheses, just the fg of x, we want to be very careful. We generally don't use the dot for multiplication because in a future video, we're going to talk about another operation that we can do with functions, and it uses a symbol that's very similar to the dot. So just to avoid any confusion at all, we don't do the dot when it's inside that single parenthesis. We just put fg, right? Because when we have at least one variable and the two things right next to each other, the assumed operation is multiplication. I also want to point out for these functions that this is not like f plus g and then times x. These are the functions at that point x. So we just simplify the functions as much as we can, and then that's it. And let's not forget our quotient function, f of x divided by g of x, and then we can just write it in that one parentheses f over g at that point x. In general, the domain for the sum, difference, and product will have the same domain as any restrictions on either of the given functions. The quotient function is going to throw us for a loop because now we have something in the denominator that could potentially be 0, which isn't allowed. We can't divide by 0, so we would have a further restriction on our quotient function for any values at all that would cause g of x to equal 0. Let's look at some examples. All right, first we're just going to state the domain for our given functions. F of x, that's a linear function, right? There's no exponent, and we have an x, and we have a constant. And the domain of any linear function would be all real numbers. So we're going to say domain of f of x. And you can either write it using that fancy r, or I like doing interval notation. G of x also happens to be linear. It's a little bit backwards, right? We might want to write it or think about it as negative x plus 3. But regardless, it's a linear function, no restrictions. So the domain of g of x will also be all real numbers. This also means that the domain for the sum, difference, and product functions will all be all real numbers. We shouldn't have any restrictions when we combine these. Okay, so now we're going to look at a few different things. So because addition is commutative and multiplication is commutative, it doesn't matter which way we order them, the end result will be the same. But for subtraction and division, that's not the case, right? We end up with subtraction, we end up with opposite numbers, additive opposites, and with division, we end up with reciprocals. So we're just going to compare, we're going to look at each new function that we create, and then we'll state the domains. Our first one, remember this is f plus g of x. We could also think about this as f of x plus g of x. And that would be, let's see, f is 5x minus 7 plus 3 minus x. And I've added the parentheses just to show that like I'm just taking the functions and putting them together and adding them. I don't actually need them, right? The parentheses aren't doing anything. There's a plus sign between them. That's not changing anything. From here, I'm looking for like terms. I have an 5x right here and a minus x here. If I combine those, I get 4x. And then here I have minus 7 and positive 3, that would make minus 4. So our sum function is also a linear function, and it has a domain of all real numbers, as promised. Our first difference function, this time we're doing f minus g, so remember order matters here. We're going to do f of x minus g of x. And now the parentheses are not just for show, they do serve a purpose. We are subtracting that g function from the f function. My suggestion, distribute the subtraction sign and change the signs. So this becomes a negative 3, and this becomes a plus x. And then once I do that, now I can write that subtraction as addition. That's that property of we can write subtraction as addition by adding the opposite. Now I can look for the like terms. I have 5x and positive x. So when I combine 5x plus one more x, I get 6x. Negative 7 and negative 3, they're both negative. So I combine and keep that minus sign. This first difference function is also linear, and it also has no restrictions as promised. Our second one, now we're going to take g of x, and we're going to subtract it by f of x. So g of x is 3 minus x minus 5x minus 7. And just like the first subtraction function or difference function, I want to distribute the subtraction sign. That becomes a minus, and this minus becomes a plus. Once I do that, I can rewrite that as plus. Now I can look for those like terms. I'm going to start with my x's, right, because that's kind of the more normal thing. We have negative x and negative 5x make negative 6x. 3 and 7, they're both positive. They make positive 10. I mentioned earlier that when we switch the f and the g in the difference functions, they should be exact opposites, which we can see that they are. But we still have a domain of all real numbers. Next up is our product function. We're going to multiply the function f by the function g. When I do this, I will have to put them both in parentheses because we have a binomial times a binomial. However you want to do this, if you want a FOIL, distributive property, whatever way you want to think about it. 5x times 3 is 15x. 5x times negative x is minus 5x squared. Minus 7 times 3 is minus 21. These are in a very weird order. And minus 7 times minus x, negative times negative is positive 7x. I'm just going to rewrite these and combine like terms because this is really weird. Our first term, we're going to put that x squared. We have a negative 5x squared. Then I have 15x and 7x, which is 22x. And then I have this minus 21 all by itself. And there is our product function. So the product function is not linear. This is a quadratic. Largest exponent is 2. We finally have something different. However, the domain is not different. It is still all reals. Our first quotient function, so this is f of x over g of x, right? This is the function f over the function g. And this would be 5x minus 7 divided by 3 minus x. There's not much more we can do with this quotient function. We can't simplify. There's no like terms, nothing of that. We can't factor anything. But there is going to be a problem with the domain because now we have a restriction on x. The denominator cannot be 0. So what would cause the denominator to be 0? Well, if I added x to both sides, I would have that 3 cannot equal x. So the domain for this quotient function will be negative infinity to 3 and 3 to infinity. So it's like we're taking those real numbers and we're just plucking out 3 from them. Everything else gets included. Sorry, 3, you didn't make the team. And our last example of this first example, we have the other quotient function, g over f. Now we have 3 minus x divided by 5x minus 7. Again, we can't simplify this. We can't factor anything. That just is the quotient function. We have a new restriction because now we have a denominator of 5x minus 7, and that is not allowed to be 0. I add 7 to both sides, so I get 5x can't equal 7. Divide both sides by 5. And it turns out here, x can't be 7/5. You could also write this as 1 2/5 or 1.4. I'm totally happy with my improper fraction. I will leave it. I'll write my domain in interval notation. We can go from negative infinity, anything at all between negative infinity and 7/5, just not 7/5 itself. And this was our first example. Let's look at another one. So here we're given f of x this time is a quadratic. G of x continues to be a linear written in a very weird form. In either case, the domain of each is all real numbers because that polynomial does not have restrictions. So I'm just going to say for both f of x and g of x. And let's look at those operations one more time. Our sum function, remember, this is just, I didn't write this for all of them. I only did it for the sum function in the last one too. I'll try to remember to do it for all of them. We're just adding the two functions. F is x squared minus 4, plus we're adding to it 2 minus x. Again, for the sum function, I added the parentheses just for emphasis to show where f and g were. I don't need them. They're not serving really any purpose. I'm just going to look for my like terms. X squared is on its own. X is on its own, or negative x. And then I have a -4 and a +2, which makes -2. So the sum function creates a quadratic. And this particular quadratic has a domain of all real numbers. Our first difference function, we're doing f minus g. So this is going to be x squared minus 4, there's f, minus g of 2 minus x. Oh, I said I was going to write it. Here we go. F of x minus g of x. The parentheses are serving a purpose this time. I do need to distribute that subtraction sign to the entire g function. That's going to change the signs. That becomes a minus. This becomes a plus. Right? I just distributed it, so that becomes a plus. And now I don't need the parentheses. I could drop them if I wanted to. I'm going to look for my like terms. X squared is the only one of its kind. The positive x, now it's a positive x, right? Because we changed the sign of it. And then we have finally some like terms, -4 and -2 make -6. This is as far as we need to go with this one. So we're going to end our difference function here. It's also a quadratic, and it also has a domain of all real numbers. Our second difference function, what are we expecting to happen here? It's going to look like the one right above it, but all the signs are going to be backwards. So they're all going to be switched of what we see in that previous, the one we just computed. This time we're doing g of x, this function, minus the f of x function. G of x is 2 minus x. And then we're subtracting from this x squared minus 4. Again, we must have the parentheses. We're going to distribute our subtraction sign. That becomes a minus. This becomes a plus. And then I can change that to a plus. And now I can just look at the number that, or the value that we're given, the term we're given. Here I have a negative x squared. Here I have a minus x. And then I have 2 plus 4 is 6. Does that look like the exact opposite of the one right above it? Yes, it does. That's good. And we have a domain of all real numbers. Next up on the list, we have our product function. We are going to multiply using our favorite technique, or my favorite technique, FOIL, or the distributive property. This is f of x times g of x. F of x is x squared minus 4. G of x is 2 minus x. Let's distribute. X squared times 2 is 2x squared. X squared times negative x is negative x cubed. Negative 4 times 2 is negative 4 times 2 is negative 8. And then negative 4 times negative x is positive 4x. So that just follows the FOIL technique. First, outer, inner, lasts. I don't have any like terms. How bizarre. I do want to put these in the right order though, because it's weird to not have the x cubed first. The negative stays with it, so we get negative x cubed plus 2x squared plus 4x minus 8. We now have a beautiful cubic function, and its domain is all real numbers. Last up on the list are our quotient functions. First up, we have f over g. F is x squared minus 4, and g is 2 minus x. Okay, wait. We do have that quadratic, and that quadratic can be factored. X squared minus 4, that's a difference of squares. A difference of squares will factor into root minus root times root plus root divided by 2 minus x. Now, I'm kind of getting ahead of myself here. Before we factor, or before we simplify, factoring is fine. Simplifying, we need to be very careful about, because the domain happens before we simplify. So right now, before I simplify, I'm going to pause and figure out what the domain is. Right now, with the function we're given, 2 minus x is not allowed to be 0, because then we would have a 0 in the denominator. It's not allowed. Therefore, x cannot be 2, right? If I add x to both sides, I get x can't be 2. So we do have a restriction on the domain. The domain can be any real number except for 2. We do the domain before we simplify. Now I'm going to look to see if I can simplify. What I notice is that in the numerator I have an x minus 2, but in the denominator I have a 2 minus x. I discussed this in a previous video way back when we were looking at simplifying rational expressions. Notice that those are just reverse of each other, right? 2 minus x is the opposite of x minus 2. We can cancel them, but they don't cancel totally. They cancel and create a -1. So I'm allowed to do this, and then I just have to make sure I include a -1 somewhere. So somewhere I need to have a -1 to indicate, yeah, I sort of canceled them, but they were opposites of each other. That makes -1. And then all I'm left with is this -1 times x plus 2. This is a little bizarre. I might distribute the negative and get -x minus 2 as my quotient function. And then lastly, wait, I'll pause for a minute because that was kind of a weird one. Okay, hopefully you've had some time to process. Now we're going to look at our final example for this table, the other quotient function, g over f. So g over f is going to be 2 minus x over x squared minus 4, right? It's the reciprocal of the one right above it. I'm going to factor, but then I'm going to do the domain before I simplify. So again, since it's the reciprocal, we have the same factors. This is a difference of squares. But now I have two issues in my denominator because now x minus 2 times x plus 2 cannot be 0. So we'll come over here and say this and this, neither of those can be 0. Well, this means that x can't be 2, and this means that x can't be -2. So the domain, which remember we do before we simplify, we're going to pluck out -2, but we include all the values between -2 and 2. We include all the values bigger than 2 and all the values smaller than -2. And now I can simplify. We have the same thing, right? So I have this opposite factor. We're going to replace it, just one of them, with a -1. And then I can write this in several ways. So I can have -1 over x plus 2. I can put the negative in front of the fraction. If I wanted to, I could distribute in the denominator. I think this is the most efficient way. I'm just going to leave it like this. And that's going to be my final quotient function. So with the examples that we just did, we always had f of x and g of x. Now we're actually going to look at specific points within these functions. And again, we're going to just verify that the laziness of mathematicians is just fine. We can either combine the functions first and then replace all x's with 2's, or we can replace all x's with 2's in each function and combine, and we should end up with the same result, right? Because my promise previously was that f plus g of 2 should be the same as f of 2 plus g of 2. So let's just make sure we end up at the same end result. I keep putting x. It's 2. It's 2. There we go. There's the 2. All right, starting with our first one, over here on the left, we're going to combine the functions first. So when we combine, f is 3x squared plus 2x, and g is 3x minus 1. And now we have, let's see, the parentheses are there strictly for ornamental purposes to just show the two different functions. We're going to combine like terms. We get 3x squared plus 5x minus 1. And now what we're going to do is we're going to take that sum function and replace all x's with 2's, right? We evaluated f plus g, we simplified it. Now we're going to actually compute at 2. This would be 3 times 2 squared plus 5 times 2 minus 1. That's 12, right? 2 squared is 4, and 4 times 3 is 12, plus 10 minus 1. This is 22 minus 1. Here I get a result of 21. Let's compute them separately now. So if I compute them separately, f of 2, that's anywhere in f I see an x, I'm replacing it with 2. And there I have that 2 squared is 4, 4 times 3 is 12, and 2 times 2 is 4, so f of 2 is 16. Okay, g of 2, well, that's going to be, I don't know why I keep wanting to write x. It's just ingrained in me. 3 times 2 minus 1. 3 times 2 is 6, and 6 minus 1 is 5. So when I go this way, I get 16 plus 5, which equals 21. They match. So it's really up to you. Whichever way you think is going to be better for you is the way that you should do this. We'll look at 2 more examples, and again, we'll look at both ways, but you don't have to do both unless you want to check your work. You just want to pick which one you think is going to be better for you. This time we're looking at a difference function at -1. So first we're going to combine the functions using subtraction. This is f first. 3x squared plus 2x minus 3x minus 1. I'm going to distribute my subtraction. And then, let's see, oh, that becomes a plus. So I have 3x squared. And then these two make a minus 1x or a minus x. And then we have a plus 1. I've simplified the difference as much as I could. Now I'm going to replace all x's with minus 1's. 3 times minus 1 squared minus 1. Be very, very careful about that. Order of operations says minus 1 squared is 1. 1 times 3 is 3. Here I have minus negative becomes plus a positive. And 3 plus 1 plus 1, here I get 5. What should I get when I do f of -1 minus g of -1? You bet your bottoms we're expecting to get 5 as our final result. Let's start with f of -1. F of -1, we have 3 times -1 squared plus 2 times -1. -1 squared is 1. 1 times 3 is 3. 2 times -1 is -2. And 3 minus 2 is 1. So I have 1 minus whatever I compute for g of -1. Let's see what happens. That's 3 times -1 minus 1. That's minus 3 minus 1, which is minus 4. So I'm subtracting -4 from 1. That becomes plus plus, and I get a 5. Voila, we end up at the same result as we should. We're going to test this one more time with our product function. We have f times g at -4. So first, we're going to multiply the two functions, and then we're going to compute them separately and multiply that. So let's see, we have 3x squared plus 2x times 3x minus 1. When I FOIL, I get 9x cubed minus 3x squared plus 6x squared minus 2x. That's 9x cubed plus 3x squared minus 2x. Okay, I've simplified it as much as I can. Now I'm going to plug in -4. Uh-oh, I hope I have a calculator handy. I don't. And then we have -4 squared minus 2 times -4. -4 cubed is -64. And then -4 squared is 16. And just do this step by step and really take my time. And here the negative times negative is +8. 64 times 9, let's see. 64 times 9, that's 36, 54, 576. Whew, crazy town. -576 plus 48 plus 8. There's a lot of subtraction here. You know what? I'm going to combine these because they're both positive, and I'm going to get 56. Ooh, that's much better. Then -576 plus 56 is -520. All right, so when I combine first, I get -520. Now I'm going to do each one separately at -4, and then I'm going to multiply those results together. This is f of, sorry, -4, and g of -4. There we go. Okay, so f of -4, we have 3 times -4 squared plus 2 times -4. -4 squared is 16. 16 times 3 is 48. And 2 times -4 is -8. Ooh, that's nice. I get 40. I can handle 40. Okay, so we have +40. Yep, +40. And it's going to get multiplied to g of -4, which is 3 times -4 minus 1. 3 times -4 is -12. -12 minus 1 is -13. I'm going to multiply by -13. Well, that's going to give me -520. So either way works again. These have been examples of the 4 operations and functions. Thank you for stopping by.